Hey, welcome back. FMT100 here. We're on Unit 3, or Chapter 3 as it says right here. Fasteners. This will be a fascinating unit as it was obviously delayed. I've had a few problems, got through those, moving on. And what I'm going to try and do today is literally plow through this little section here, this PowerPoint. So it's going to be one big deal. We can get through it together. I am confident in that. So what are we looking at? Well, we're going to want to define the terms that are associated with threads. There's actually quite a few. Discuss the class of a thread. No, not a class, but a type of thread. Discuss and demonstrate the proper tapping procedures and the proper method of using a cutting die, which is a lot of, well, it's fun if you got the right mindset. List several types of fasteners. Identify the grade of a fastener, and it's not A, B, or C. Use tables to determine tightening torque of a bolt, also known as torque specifications. So, threads. We see them all the time. You are going to now have a different appreciation for them, I hope, by the end of this unit. So, we've got a unified standard, also known as a unified system, and it is nothing more than a universal system that different countries all agreed to that, yes, we're going to make our threads this way. So threads from the U.S. can be used for threads in Europe and back and forth. Covers the cross-sectional shape of the thread, diameters, the threads per inch, or the pitch. The list kind of goes on. So what we're looking at is this side view of threads, and on the bottom is our bolt or our screw, and on the top is our nut or the cut threads inside a casing. So we've got a bunch of different areas here. All right. The most important ones to look at are going to be the crest, which is the top, and I don't know if I got a pointer here. Yes, I do. So one of the important ones is right here. This is the crest, and each side has one. You notice here's our nut, or like I said, our casing. So we've got a crest here, and we've got a crest here. Notice that our crests are kind of nipped, and then we've got a root, the valley, and they're nice and rounded, which is fine. So when these two are close together, the crest doesn't go all the way to the root. There's actually a little space in between, and that helps keep the two systems, the bolt or screw, from binding with the nut or casing. They got in there, that would be a lot of forces, and it would jack up the threads. We also have the thread length, and that is the distance between our root and our crest. And then we have the entire area, and that is known as the face. So we got it right here. And last but not least, we're going to look at the difference, the elevation, if you will. If you want to look at the crest as being a mountain peak and then the root as being a valley below, like you're looking at the elevation change, that's going to be the thread depth. So this is what we've got going on. These are the different parts of threads that we need to be concerned about. And one of the unique things, and I think is kind of funky even still, is that all that we just covered, the surfaces that see all the force is just the face. So that's how we're getting our forces transferred to the fasteners, is just right there on the face. So I find that interesting, as I'll say. So we've got thread series. We've got coarse thread, we've got fine thread, extra fine thread, and constant pitch. So coarse thread is just that. You'll find coarse thread typically where it's going to be really nasty as far as corrosion. You'll find coarse thread in that area. Fine thread, you'll find fine and extra fine typically in areas of high vibration. And then constant pitch you'll find in really odd places. So I'm just going to leave it at that. For me, because of everything that I've bumped into, most that I've seen is coarse thread for uh, fasteners like flange gaskets, that kind of thing. It's always coarse thread, and even when you are putting together pump housings and such like that, it's usually a coarse thread. The fine thread, extra fine thread, is usually as you go into more delicate and refined equipment. So we've got diameters we've got to worry about. We've got the minor diameter and the major diameters. Uh, the fun part is that all depends on what part you're talking about. So that's the fun part. So the major diameter for a screw is going to be on the crest. The major diameter for a nut is in the root. And then for the minor diameter is going to be on the screw root, and then the minor diameter for the nut is on the crests. Yeah, I know. You're like, what? No, I'm sorry, the nut crest. Anyway, you got the idea. This pick also in your book. So this one gets a little bit more funky, especially when we start looking at metric. Takes a little bit of a different meaning, but it'll work. So thread class 1 is loose fit, extremely relaxed, easy assemble. Once again, you'll see this also a lot where you think it's going to be really rusty. Class 1 is the way to go. Regular tolerance is just about everyday kick around what you can use, and then interference tolerance, difficult to assemble without a tool, and typically you'll find those with really high vibration. And yes, you'll typically want like a torque wrench and a few other wrenches to get these two fasteners going. So metric threads, it's the M profile. Yes, as U.S. has become more involved, or finally opening up to global commerce, and as we get more and more involved, so we're going to see a lot more metric. The M just means it's metric, and we're looking at a pitch measurement in millimeters, and the pitch is from center line of one thread to the other thread, and we're also looking at the diameter, and they have a pitch diameter, which is the next slide here. So here's the pitch diameter. And if you were to take an invisible imaginary cylinder, slide it down in this case, the nut, where that diameter cuts our face equally in half, that would be the pitch diameter. So when you ask for like a 8mm screw with a 1.25 pitch, that pitch diameter is 8mm. That's what you're asking for. So if you were to measure it with calipers, it's going to be a little larger, and if you were to measure the nut, it'd be a little smaller. So keep in mind, we're looking at that imaginary cylinder that's cutting that face equally in half. Taps and dies, some of the most, well, at times can be expensive and most frustrating pieces of equipment and tools to use. So taps and dies are made out of material that's harder than the material they're cutting. Usually it's high carbon steel, and then they go to really stupid holy crap alloys when you're trying to tap and cut stainless steel. It gets really insane, really expensive real quick. The fun part is the parts that are actually doing the cutting are called lands. As it says, it does the actual cutting. Now the flutes, not a musical instrument, it's the space, literally, it gives the place for the removed material to go to. All right, because if not, the lands would bind up, they would get gummed up with all the cut material. It would freeze up the die or the tap. You'd use too much force, and then you would end up breaking the tap or the die. The harder the material, the more brittle it becomes, and so it's not as durable, and it breaks easy. So flats, this is the first time I've ever heard the term used. So used to turn the tap or die. Um, I've always been told it was wrenches or handles. So, and there are special handles to use taps and dies. Don't use a crescent or adjustable or whatever. Use the proper handle for your tap and die. They're expensive. That's why I'm harping on it. And it's easier to use the proper handle, especially when you're doing taps, because here we go. We got a starter tap or taper tap because we've got a really nice long taper on it. It's easy to get this tap into the hole, and so you can keep the tap a lot easier in a full 90-degree, so it's perfectly in line with the hole as you start cutting the threads. Plug tap, I bounce back and forth. I still like plug taps. It's not as severe as a taper, but with practice, you can use a plug tap to start a hole to get it threaded, and away you go. Um, I have only a few bottoming taps, and these have like no taper. I think it's technically there's two threads that are tapered or chamfered. That's it. These you cannot start. I don't care what anyways. You cannot really start efficiently a hole getting it threaded by using a bottom tap. You usually start with either a starter tap or a plug tap, and then you finish off with a bottom tap. Um, and as it says, a bottom tap is you're going to use it in a blind hole, because if you use the other two up top, because of the taper, you're not going to get threads all the way to the bottom. Only a bottom tap has the threads that go all the way to the bottom. So there you go. Have a video for you guys. I hope you already saw that on how to use a tap. Working on a die is roughly the same way. You got to make sure your die is perfectly perpendicular to the shaft that you're trying to cut the threads on. You got to make sure the shaft is properly sized to fit the die. And for the love of everything that's going to make it easy, please use plenty of cutting oil and put something underneath this cutting process, because the oil is going to drip and you don't want to have any slippery areas. So just throwing it out there. So fastener types, what do we got? Well, for threaded stuff, we've got bolts, machine screws, threaded studs, and double-ended studs. Oh, let's get to the most numerous right off the bat. They didn't. So bolts come in pick array of sizes and thread pitches and whatnot. Machine screws are the same way. There's new ones always being designed and developed. Good gravy. They're all over the place. Traditionally, bolts were used with a mating nut, and you would screw the nut and bolt together. Machine screws were traditionally used to keep housings together. You would screw in a machine screw to a pump housing. Well, things have changed. We now use machine screws and nuts, and then we use bolts to keep housings together. So now nuts and machine screws are pretty much used interchangeably. Anymore, it's really hard to define which one's which. So just so you know, some would say, well, a machine screw is usually smaller. All right, fine. If you can use a Phillips or flathead, then yeah, it's probably a machine screw. But it gets fuzzy from there. Nonetheless, both have threads that usually go all the way from one end up to the head. There may be an area that is not threaded, that's known as a shoulder, and that's where you typically want your flange or your piece of material to rest, so you're not damaging threads. So just so you know, depends on what you've got and what you're working with. Threaded studs, also known as all thread. Yes, it's cut to fit right here. All thread, typically it'll come either pre-cut as 6 to 24 inches, and then it goes stupid. You can start at 24 inches and then go all the way up to 96 inches. And now you're just cutting with a hacksaw the length that you need. I mentioned before on the page, when you're cutting all thread, and there's nothing wrong with cutting it with a hacksaw. In fact, hacksaw is probably going to be your best way to go. You've got more control and you'll have a straighter cut. But mark the length of the stud that you need. Take 2 nuts, screw the nuts down to your mark, and then bracket the mark. Have a nut on either side of that mark. Leave enough room so you can properly work your hacksaw. And then saw your all thread. And now unscrew your nuts towards the cut of that all thread. And what that does is help clean out the threads. So now you can easily take on and off nuts from that now trimmed all thread. Now you may still want to chamfer the edges of the threads, so it's even easier, but definitely if you use the nuts to clean out the threads, your day will be a lot happier. The first time you forget to do that and try and cut and then put nuts on your cut all thread, you will be cussing the day. I've been there. I'm just trying to prevent some pain and frustration for you. That's all I'm trying to do. Double-ended studs, these are usually pre-manufactured. You would almost think that they're all thread, but they're not. They are usually pre-cut links. The smallest I've seen is 2 inches, and then they go up to, typically I've seen only like 12 inches, but I know I want to say they go up to 24 inches, talking around. And what they've got is they've got threads extending up a inch or a few inches up the stud, and then it stops, and now you have a shoulder. And once again, that shoulder is where your material is supposed to rest. There's supposed to be some threads that go into the material or below the material surface, so that way as you stretch out the stud, you still have threads and you're not trying to cut threads with the nuts. That's a no-no. So you're not trying to cut threads, you're trying to just get everything properly tensioned. With the all thread, when I said you're backing off the nut, once again, you're not cutting threads. You're clearing them, yes, but you're not cutting new threads with the nut. That is considered bad form. The all threads you'll find in a lot of installation when you have to hang stuff. A lot of places are now using all thread for that in conjunction with Unistrut, and they do that for all the seismic retrofit stuff. You'll see that often in HVAC equipment being hung and other equipment being hung that way. And once again, the double-ended studs, you'll see that a lot in industrial piping when you are joining 2 flanges together. So just so you know what's out there. Pin fasteners, dowel pins, taper pins, split pins, clevis, cotter. They have really great examples on the pages and in the book and whatnot. I gave you a couple of ones as well. Dowel pins. Dowel pins are nothing more than a means of guiding and what they call registering the parts of 2 casings together. All right, so all these are positioning pins, and that's it. They don't really serve any true fastener. I mean, they don't add any strength to the component. They just literally position. Taper pins, on the other hand, are used to join and can be used to position, but they are used to join 2 pieces together, and you drive them in, and as they taper, basically you're using wedge force to keep the 2 pieces together. Not a big fan of them, but they're out there, and you got to use what you got to use. Split pins. Holy crap, you got a different full gamut of these things. Typically, they work into 2 classes where you've got a almost looks like a rivet, but it's either got a flat or rounded head, a shaft or shank, and that shaft or shank has been cut, split down the middle, up to about halfway, and you put the split pin through your two pieces, and then you flay the cut sections open. All right. Now, there's the roll pin. Now, roll pin is, or the split roll pin. And these are interesting. They're usually done out of spring steel. They've got chamfered ends, and it is hollow. So it's a hollow pin. It's technically rolled flat metal that they've made into this rolled pin, hence rolled pin. And you delicately drive these pins into the hole, and as you are driving them, the split gets compressed, so that little distance closes, because now you're using the rolled pin as a wedge, and as you're driving it in, the pin itself is being compressed, but the pin is also pressing against your two pieces, two parts, whatever, and keeping them together once again with this wedge type action. You definitely need a drift punch and a machinist hammer when you are working with rolled pins, rolled split pins. Clevis pins, nothing more than a nice straight shaft or shank. You've got a flat or round head on one end, and on the other end, drilled perpendicular to the shaft, is a hole of which a retaining clip goes through. Or a cotter pin. Cotter pin looks like a hairpin, usually made with either flat, half round, or round metal stock, and it looks like a hairpin with a nice bulbous end, and then I call them legs. Work with me. The two long legs will slip through the hole, and then you splay the ends out on the other side. If you put a cotter pin through a round stock, you tend to take the ends and you roll them around the round stock, keeps them out of the way, and you know the pin's not going to fall out. If it's a flat surface, you try and keep the pins as flat as you possibly can. Here is an example, and like they're doing here, they've got the two ends, and they're going to flatten them out. They're going to splay them and flatten them out, try and get as flat as they can to the surface there. Can't get it too flat because that is a stressor, but this would work right here. You do not want them straight out like this, or even at a 30-degree angle. You want it greater, so it's a lot more surface areas there. Grade markings. Grade marking is nothing more than a means of indicating the strength, the tensile strength of our fastener. And nope, I don't have a deal here to show you because it would take up most of the damn screen, and what a pain in the butt that would be, and even then you couldn't see it all that well. So please look at the book. It's figure 314. I do have a little bit on the web page for it, or the Canvas page for it. In case you're wondering, it is the American Society of Testing and Materials that does the grade markings, as well as the Society of Automotive Engineers. Yes, Society of Automotive Engineers does a lot of our bolts, because holy crap, there's a lot of bolts that go into a car, specifically a car's engine. So that information is now shared throughout the rest of the industry, and we get to use it as well, which is pretty nice if you ask me. So, and real quick, you'll find the markings once again on the heads of your bolts, and even on the sides of some of the screws. So torque specifications. So torque specifications, what we're trying to do is we are trying to get a particular length, a particular force within our fastener. And we've got a couple. We've got initial tension, which is still a force, but this force is created from the tightening of the fastener. We're still stretching out the fastener, but we're doing it in a twisted action, typically with our retaining nut. And then preload, which is a clamping force, and that is definitely stretching out our fastener. In particular, think of our bolts and our machine screws. Either one will still get the same effect. And all we're trying to do is we're trying to make sure that we have enough force inside that fastener that we're keeping our two pieces of material, our two parts of a machine, together regardless of the operating conditions going on in the machine. That's all we're trying to do. If we do not have enough internal force, notice I said internal, not initial, but internal force within our fastener, those two pieces of metal, the two pieces of our machinery, are going to be able to move about. They're going to shift. And that shifting could be very, very bad depending on the operational stress loads that the machinery creates. So we want to make sure that we prevent that movement. And we can either do that through an initial tension, which again is the tightening of the fastener, or the preload, the clamping force. The book, I really like the book because they go over rather quickly. One of the ways you can do that is you heat up the bolt, and as you heat up any material, it lengthens, right? We heat something up, it expands. If we cool something down, it contracts. Well, in this case, we're gonna heat it up, and we're gonna heat it up to a particular temperature. And depending on the application, they will have a pyrometer. Think of a high temperature thermometer, and they will place it on the bolt to make sure it's at the proper temperature. Then they will take that bolt and they will insert it in the machinery, screw it down, turn it, tighten it, whatever, and then they'll give it another prescribed twist to make sure that they know everything's fully seated, and they will let that bolt cool down. And as that bolt cools, it's going to shrink, it's going to contract. Well, as it's doing that, it's creating that internal force, that internal tension that's going to clamp the two pieces together. You'll see this every once in a while. I'm a huge railroad fan, so you'll see that also when they rebuild boilers. They'll take the rivets for the boilers of steam engines, and they will heat the rivet up, and they're heating up to a particular temperature again. And when they get the pieces of the boiler together, they put the hot rivet in, and then they'll round the other side, and they'll make sure that it's all properly compressed. And then as that rivet cools, it's going to shrink, and it's going to pull the two pieces of the boiler together. And that way the two pieces of the boiler don't move, and away we go. We know we've got the proper clamping force. The other area that you'll see this, because I also enjoy Art Deco, is some of the older buildings. Think of the Empire State Building. That was made with hot rivets, and it's the same principle. The other place you'll see this is in some of the old railroad trestles, because that's easy to see. And if they're not using the hot rivets, they're going to still be using nuts and bolts, and those are also going to be tensioned either with initial tension or with the heating method, so we can get to make sure we've got the proper clamping force. All looking for the same deal. In worst case scenario, we can still use a torque wrench, and we can go from there. So the importance with that is we need to make sure we put in enough torque. If we don't have enough torque, things get loose, and they either shift, like I was talking about before, and they shift and they rub on that fastener, and you can usually tell that when the threads are worn away, or if the fastener has been deformed due to shear. So shear is, think of when we're using scissors, we're using a shear force to cut the paper. Take that same concept, put it on our larger scale, and we now have two pieces of metal, big heavy metal, and we are having those two pieces of metal slide against each other. If the fastener is in the way, the fastener becomes the piece of paper and will get cut. It's one of the reasons why we need to make sure we're using the proper grade of fastener, because it has the tensile strength to resist that shear force. And we also want to make sure we have enough torque, enough clamping force to make sure those two pieces of metal do not allow themselves to move, to shift, to create that shear action. On the other side, if we put in too much force, we could actually fracture the shank of our fastener. We could shear it. We could shear the head right off of it. That's always fun. You never see engineers cuss more when that happens. Or we could strip out the threads or of the fastener or even the nuts. So we could strip those out. So we need to make sure we put in the proper torque. Now, most manufacturers will give the proper torque and the means of getting there. All right, so we have to look out for that. In a worst case scenario, we can always go, if we're just doing the general stuff, we can go to a standard torque specification chart and use that. The catch is most torque specifications are for no lubricant, no coatings at all. If we start putting coatings on the threads, for us, we had to use a high temperature anti-seize on our threads at the refinery, because if not, because it was so hot, the threads would heat up and gall, and they would stick to each other. So we put this high temp paste on. It was an anti-seize, so it would prevent the galling. But we now had to modify our torque specifications. So because of that, so it's rather insane. And here, so we go through, we look at no lubricant, and we got 0% of the recommended. Let's go for where it is. Let's go for graphite and oil. That's in a way kind of what we were using. So graphite and oil. So we take our torque specification and we multiply it by 0.55. That's 55%. And you're like, well, wait a minute. If we're multiplying our torque spec by 0.55, our torque's going to be less. And yes, it is. Because we're not going to need as much torque to get our fastener to move, to get it to stretch. Because we basically have added a lubricant. All right? So, because we've added this lubricant, we're going to have an easier time stretching that bolt out. And if we stretch it out too much, once again, we run the risk of shearing, stripping out threads, that kind of thing. So that's why it's really important to look at what your torque requirements are, and if you need to do any modifications to that torque value. Fortunately enough, retaining rings typically don't run into that problem. So we've got internal, external snap rings, as you saw on the page for it. I did them as one. They kind of look the same, but not really. The internal snap rings are perfectly round on the outside, and then you've got the little dip, the two nipples, dimples, whatever, so you can get the snap ring pliers in to remove that snap ring. The external ring is perfectly round on the inside, so it can slip over the shaft. Internal snap rings go inside, so that's why you want the perfectly round. If it's perfectly round on the outside, it's an internal. If it's perfectly round on the inside, it's external. Makes perfect sense, right? Not. Use them a few times, you'll know it. Okay, just please believe me on that. Then we've got crescent clips and E-clips. These are a stretch of the imagination because they both look like the namesakes. The crescent looks like a crescent, and the E-clip looks like a stylized E that's been squished. So there we go. Here, this is what an E-clip looks like. It looks kind of, like I said, it looks like a stylized E, an uppercase E that's been kind of squished. There we go. Now, for both the E-clip and the crescent clip, to remove these things, you're going to have to push on each side of our clip here. You're going to push both these ends so you can get enough space off the shaft to get a flat bladed screwdriver in. Now, that's going to be really important on a crescent clip because you don't get a lot of space. But if you notice here, if you look at an E-clip, you've already got a little space. So you can get a flat-bladed screwdriver in here and twist. Notice I didn't say pry, I said twist. Twist the screwdriver, and that will help pop this E-clip off. The catch is obviously where eye protection, this stuff can fly off really fast, and it hurts like hell just to get popped in the face with one of these. I don't even want to think about how bad it would hurt to get hit in the eye. And if you can keep a hand over it when you're doing this, that way you can try and catch it, or at least it doesn't go flying off into the great void. I've got great news for you. The next slide looks like this. I should find a way to put end credits on or something like that. Hey, we made it to the end. Plowed through this real quick. There is no lab on this one. I'm using the torque wrench as our lab, the video for the torque wrench as our lab, and so no lab on this one. Take a sigh of relief, and in the meantime, I will catch you on the flip side, so keep hanging in there, and I will chat with you all later.